Today's daily code problem of the day is Stone Game Part 2, number 1140. For this problem, Alice and Bob continue their games with piles of stone. There are a number of piles arranged in a row, and each pile has a positive integer of stones in it. The objective of this game is to end with the most stones. So Alice and Bob can take turns, with Alice starting first. Initially, the m value is equal to 1. On each player's turn, that player can take all the stones in the first x remaining piles, where 1 is less than or equal to x, which is less than or equal to double whatever the m value is. Then we can set m equal to max of m or x. The game continues until the stones have been taken. So we want to assume Alice and Bob play optimally and return the maximum number of stones Alice can get. Basically, what this is saying is we are going to have to traverse it from left to right, where Alice can initially either take 1 or 2 stones. So Alice can either take this 2, or she could take 2 and 7. However, when it's Bob's turn, if Alice decides to take 2 and 7, Bob can decide to take the rest of the stones, because he has the option to take anywhere from 1 until 4, or 2 times m. And m would be equal to 2, since Alice did take 2. So, if we look at the explanation here, if Alice takes 1 pile at the beginning, so Alice only takes 2, and then Bob takes 7 and 9, and then Alice takes 2 again, the remaining 2, Alice can get a total of 10 piles, which would be the output because that's the most that she can get. So down here, if Alice takes 1, Bob takes 2, Alice could take the remaining 3. Somehow that would be greater than what the output is. So for this second example, Alice would take 1, Bob would take 2, Alice would take 3, Bob would take 4 and 5, and then Alice would take 100. Doesn't necessarily make sense, but it works out. So for this problem, we're going to do it in Python, and we're going to take a dynamic programming approach. This approach is going to use memoization. So we're going to first choose between 1 and 2m piles of stones. Then we're going to recursively explore the options and use dynamic programming with the memoization, find the minimax and the suffix sum optimization, and recursively solve this problem. So, first things first is we can identify an array called memo is equal to 0 times the length of our piles, and then we're going to fill it for blank in range of length of piles. We'll then have our suffix sum, which is going to be equal to piles of piles of everything. So then we're going to compute our suffix sums. And that just means we're going to go through our entire length of our piles and calculate our suffix sum. So for I in range of the length of our suffix sum minus 2, -1, -1, we're going to have our suffix sum of I be equal the suffix sum of I plus 1. So basically we're just traversing it backwards and adding on to it as we traverse it backwards. And remember, we already copied our piles array to our suffix sum. So suffix sum is currently equal to piles. However, we're continuously adding the previous element the element after our current element to our current element. Then we are going to go ahead and call to a helper function. This helper function is going to do all the recursive solving for us. So we can return our self.maxStones, passing our suffix sum, 1, 0, and our MIMO. So now we can define our max stones, which is going to receive our self. It's going to receive suffix sum, which is a list. It's going to receive max till, and then it's going to receive the current index, and then it's going to receive our MIMO. So 1 is the current max taken, and 0 is the current index. MIMO is our MIMO array, suffixes are suffix sum. Then we can check if the current index plus twice the max index exceeds the array size, take all the remaining stones. That's the most optimal solution. So if current I plus 2 times max till is greater than or equal to the length of suffix sum, we can return suffix sum of current index, current I. And remember, each index of suffix sum is that index plus everything that came after it. So we basically went through piles and looked, okay, so 4, and then this index is equal to 4 plus 4, and then this index is equal to 9 plus 4 plus 4. This one's equal to 7 plus 9 plus 4 plus 4, so on and so forth. So returning current index here returns, let's say it's 9 right here, would return 9 plus 4 plus 4. We can then return the MIMOized result if it exists. So if MIMO of cur I of max till is greater than 0, then we can return our MIMO of our current I of our max till. So for our MIMO, we're basically just checking if the current index and the max till have if they have a difference of our suffix sum and our result that denotes a maximum amount of stones that can be picked, we will pick it. That will be solved later on in our algorithm. So after that, we can then check if we're going to find our new minimum value for our result in our next move possible. So we're going to have an integer result, which is going to be equal to integer dot. Sorry. We're going to have our result, which is going to be equal to a float, which we can equal to infinite, because we want it to be equal to a max value. Then for I in range 1 to 2 times our max till plus 1, we can change our result to be equal to the minimum of our result and self.max stones. So we're going to recursively look for a new minimum. Suffix sum, and then we're going to update our our max till. So max till is going to be equal to the max of I and max till. We're also going to have our current index plus 1 plus I and our MIMO. So that is going to constantly be updating. After that, we are going to memoize our result at the current suffix sum. So we're going to memo our current I and our max till equal to our suffix sum of our current index minus our result. And then we can return our memo of current index and max till. So if we run this, so this passes our test cases, and if we submit it, it passes all solutions. So thank you, and follow for more daily LeetCode solutions.